Hi. Let's start with a brief summary of the symbolic notation for the divergence and the curl of a vector field. Recall the del operator shown here. It looks like a vector, but be aware that it isn't a vector in the usual sense. Its entries are differential operators, instead of numbers or functions. Now suppose f is a vector field, its entries f1, f2 and f3 being functions of x1, x2 and x3. The del operator can act on f by using the formula for the dot product or the formula for the cross product, in which a product of an operator and a function, in that order, is always understood to mean the result of the action of the operator on the function. Here we go. The dot product of the del operator and f is the expression shown here, which is known as the divergence of f. Alternatively, we can form the cross product of del and f, shown here. This vector is known as the curl of f. Note that in both formulas the del operator is written on the left-hand side. What happens if we reverse the order of the del operator and the vector field f in these two formulas? Let's find out. The dot product of del and f in that order is equal to the divergence of f, which is a scalar function. On the other hand, the dot product of f and del in that order is the expression shown here, which is not a function but a differential operator. Hence, the two products are different objects. So, a dot product involving the del operator is not a symmetric operation. That is, it doesn't satisfy the rule a dot b is equal to b dot a that we are used to for ordinary vectors. Now, take a moment to think about this operator. Does it ring a bell? Recall the concept of the directional derivative of a function f in the direction of a unit vector u, which you have seen to be equal to the expression shown here. This can be written as the formal product of the single differential operator shown between brackets and the function f. This operator is equal to the dot product of the vector u and the del operator. Now, let's have a look at the cross products. The cross product of del and f in that order is equal to the curl of f, which is a vector function. On the other hand, the cross product of f and del in that order is the expression shown here, which is not a function but a differential operator. So again, the two products are different objects. So a cross product involving the del operator is not an anti-symmetric operation. That is, it doesn't satisfy the rule a cross b is equal to minus b cross a that we are used to for ordinary vectors. Finally, let's have a look at the product f cross del dot g for two vector fields f and g. F cross del is the expression shown here. Hence the dot product of f cross del and g in that order is the expression shown here. By expanding the brackets, we find this to be equal to the scalar function shown here. Now here comes an interesting twist. By rearranging the terms, we find that the function is equal to the expression shown here, and this expression is equal to the product f dot del cross g. Does this expression actually remind you of something? It has the same structure as the scalar triple product of three ordinary vectors. This product has the property shown here. The similar expression f dot del cross g does not have this property. Why? Well, first of all, it's easy to check that the two functions shown here are indeed not identical. Secondly, the third expression shown here is a differential operator, which is not a function. That's it for now. To conclude, Whenever you encounter an expression with formal dot and/or cross products that involve the del operator, always first determine what it actually means and be careful in using rules of calculation that you know from ordinary vector calculus.